All right, so the topic today is matrices corresponding to unitary and orthogonal operators. So we have proved some results about the special kinds of operators. And today we will see how those properties manifest at the level of the matrices and some matrix-specific properties also related to it. All right. So let's begin with the definition corresponding to the definition of orthogonal and unitary for operators. So there is, as usual, an analogous definition for matrices. So we will say that a square matrix A over some field of scalars F. So such a matrix A is orthogonal if we have that A transpose times A, so just multiplication of the matrices, yeah, is the same as A times A transpose and is equal to the identity matrix. Okay, so as you can see, this condition corresponds to one of the equivalent conditions for orthogonality that we have proved for orthogonality of an operator. Remember, we had this that A for example, for linear operator, T composition with T adjoint equals T composed with T adjoint equals the identity operator. So this was one of the equivalent conditions, right, for orthogonality. And similarly, we will say that such a matrix A is unitary. Oops. So the matrix A is unitary if we have that the conjugate transpose of A times A is equal to A times conjugate transpose or adjoint is equal to I. Okay. So orthogonality corresponds to the case when we just take the transpose, and unitary corresponds to the case when we have this equality with conjugate transpose or adjoint of a matrix. All right. So we have these two kinds of matrices. Let me make a remark which connects it to the corresponding properties of the operators. So as usual, by theorem 610, we have that a linear operator TLV is unitary or respectively orthogonal if and only if we have the same property for the matrix representing T with respect to beta in the sense of the definition we just made for matrices. So T beta is unitary, respectively orthogonal for some orthogonal basis beta for the inner product space V. Okay, should be orthonormal, excuse me, here. So remember, conjugation corresponds to transposition of the matrix representing it when we have an orthonormal basis. Okay. So we have this correspondence between these properties of matrices and the properties of the linear operators, which they represent with respect to some orthonormal basis. Okay. This is remark one. We also have some more observations that I'd like to record. So we have remark two. So first of all, assume A is a matrix, a square matrix. Okay, so let say A belongs to F, not F, excuse me, M n by n over F for some field of scalars F. Then we have the first observation is that the product A times A star, this product is equal to the identity matrix. Okay, this is equivalent to saying that the rows of the matrix A form an orthonormal basis for the space Fn, okay? And since we have delta ij, so remember this is the Kronecker symbol, as usual, it is equal to 1 if I is equal to j, 0 if I is not equal to j. So the entries of the identity matrix correspond to the values of the Kronecker symbol, right? This tells us that we have 1 on the diagonal on the entries of the form ii and zeros on all the other entries. So this is just the corresponding entry of the identity matrix. Okay, by assumption, this is the same as the entry of the product. So the matrix given by the product, A times A star, the corresponding entry ij, since we're assuming this equality, right? So we have the entries given by this. Now, if we spell out the corresponding entry of the product, this is the same as the sum overall k from 1 to n, the entry of the matrix ai, k, right, times the corresponding entry of the matrix A star. So here it should be kj, right? Just uncovering the definition of the product of matrices. Okay, but now we also know that the entries of the conjugate transpose can be written explicitly. So this is given by the sum overall k from 1 to n, aik remains unchanged. And here we have ajk, this corresponds to taking the transposition, and we take the complex conjugate. Okay, this gives us the entry, the corresponding entry of the matrix A star. Okay, so we have that this holds. Okay, and moreover, the last term is the so this last term here. This is the standard inner product of the rows, right? So this is the standard inner product of the ith and jth rows of the matrix A, right? So we have this observation. And the second remark, well, the second part is that similarly, we have that A star A, so the product in the opposite order, is equal to the identity matrix. This is equivalent to saying that the columns as opposed to rows. So in this order, we have the columns of A form an orthonormal basis for Fn, right? Okay, so we have these two remarks. And the argument here is the same, just you take the product in the opposite order. Okay, so so this gives us some of these basic properties. Now we have the following definition. Okay, and this maybe will remind you also something about diagonalizability that we've seen before and similarity of matrices. So we will say that a matrix A, an n by n square matrix over F is unitarily, respectively, orthogonally equivalent, okay, to another matrix, so to a matrix B in of the same dimensions. Okay, if there exists a unitary or respectively orthogonal matrix P n by n matrix over F, such that if we can write A as the product of the form P star times B times P. Okay, so that's the definition. When the matrix A is unitarily or orthogonally equivalent to a matrix B. Okay, as you can see, it's a bit analogous to the definition of similarity of matrices. But here, instead of saying that we can take a product like this with by the diagonal matrix, here we require a unitary or orthogonal matrix so that we can get this equality like this. Okay. So the first point about this definition, so this is remark 3. So the first claim about this definition, as the name suggests, is that it is an equivalence relation. So this is an equivalence relation on all n by n matrices over F. Okay. So let me remind you what we mean by an equivalence relation. So we say that this is an equivalence relation if this relation, being equivalent to, satisfies 3 axioms. So first of all, we must have that each matrix is equivalent to itself. This is called the reflexivity property of equivalence relations. Second, we have that if matrix A is equivalent to matrix B, and the matrix B is equivalent to some other matrix C, then A is equivalent to C. This is called transitivity. And we also have symmetry. We said that if A is equivalent to B, then B is equivalent to A. Okay, so relations with these 3 properties are called equivalence relations. Yeah, they play a very important role in many areas of mathematics. But here, let me just remark, so this is indeed an equivalence relation. And the proof of this is actually going to be on the next homework. So a proof of this, see homework. So it will be up to you to figure out how to demonstrate these properties I've just mentioned. But they will be stated in the homework precisely. Okay. All right. So we have this. And the first serious result about these notions that we have is the following. This is theorem 619. So assume we have a matrix, n by n matrix A, over the complex numbers. So the entries are the complex, some complex numbers. Then we have that A is normal. The matrix A is normal. Remember, in the usual sense, so normal means that taking the product with the adjoint in either order is the same, right? So it commutes. Okay, so the matrix is normal if and only if we have that A is unitarily equivalent to a diagonal matrix. Okay, so we have this new characterization of normality for a matrix that it's equivalent unitarily to some diagonal matrix. All right, so let's see. And the proof will hopefully explain why this is happening. Okay, so since it's an equivalence, we have to prove 2 directions. So first we have to show that being unitarily equivalent to the diagonal matrix implies normality. All right. So let's just use the definitions. So suppose that the matrix A is unitarily equivalent to some diagonal matrix. So what does it mean by the definition we just made? So it means that A can be written as P star D P for P some unitary matrix and D some diagonal matrix. Okay, and our task here is to show that A is normal. So what does it mean? We have to check that A times A star is equal to A star times A, right? Okay, so let's look at this. So we have to understand, calculate A times A star. Okay, so let's just substitute this expression for A and A star. So we have A is equal to P star times D times P, right? And here we do the same. So A is P star times D times P, and then we have to take the conjugate of this, the adjoint of this, excuse me, or complex conjugate of this. Yeah. Okay, so we have this. Now let's use the properties of the adjoint operator. So this is, as usual, Theorem 611, which summarizes the very basic properties. So here we have the same, unchanged, p star times d times p. But for this now, let me just remind you that if we have the product of two matrices, A times B, and we take the adjoint of them, so this is the same as B adjoint times A adjoint, right? And this can be iterated. So let's apply it now to this expression here. So this is the same as, so we get P star times D star times P star star, right? So we change the order and we apply the adjoint to each one, but in the opposite order, we take the product now. Okay, so this in turn is equal to, so this is the same, P star times D times P. But here we know that the double adjoint is just P itself, right? So this is equal to P. So what we get is, again, this is again by Theorem 611. So we get P star times D star times P, right? Okay, but now let's, so we have these two products and we're taking the product of them, right? So let's multiply everything now that we have here. So this gives us P star, D, P, P star, D star, P, right? Okay, so product of a bunch of matrices, but let's note something. So note that here we have P times P star. And remember that P is assumed to be a unitary matrix, right? Hence, using unitarity, we can, well, yeah, so let's utilize unitarity here. So again, let me go back for a second if you want to see the definition. So unitary means that the product in one order is the same as the product in the other order, the same as the identity, right? So then this tells us that this is just the identity matrix. Okay, so we can just exclude it from the product. So we have P star times D times I times D star times P, right? So here I as P is unitary. Okay, so we have this product now. Okay, and so we can remove the identity matrix because it doesn't contribute anything. So we have P star D, D star P. Okay, that's the expression for A times A star. And now we need to look at the product in the opposite direction. So similarly, we have that A star times A is equal. So you do the same thing, you substitute, and then you cancel some terms out. And what we get is that this is P star, D, P. Okay. So this product has D times D star, and this one has D star times D. So in principle, the order is the opposite. But remember that D is a diagonal matrix, right? And since D is a diagonal matrix, right? So we know that this order then doesn't matter. So we know that D times D star is equal to D star times D for a diagonal matrix. And so we conclude that the two products are equal, right? So we get that A times A star is equal to A star times A. And this means exactly that A is normal by definition of normality of a matrix. Yeah. Okay, so this shows one implication. Now we have to prove the opposite implication. So let me pause for a second if you have any questions. Okay, if not, let's do the opposite implication. So now we will assume that A is normal. Okay, and we need to show that A is unitarily equivalent to some diagonal matrix. So this time we go in the opposite direction. We assume A is normal, and we have to find P and D like we had here, so that the same condition holds, right? Okay, so let's try to do this. So first of all, we use some of the previous results that we already know. So consider the linear operator LA. Okay, so this is a linear operator corresponding to multiplication by the matrix A on the space Fn, right? So we assuming A is an n by n matrix, as in the statement of the theorem here, right? In fact, it's even Cn, right? Because F is C. So let's put Cn here. Okay, so consider this linear operator. Now, applying theorem 616 to it. So this is a normal operator because the matrix is normal. So by that theorem, then we know, since the operator is normal, there exists an orthonormal basis beta for C to the power n for this inner product space consisting of eigenvectors of the matrix A, right? Okay, so by normality, we have a basis consisting of eigenvectors. Also, by theorem 223, so this is the result from 115a, we know that in such situation, we can find similarity, right? So we know that the matrix representing A with respect to beta, which is a basis consisting of eigenvectors, can be written as A times Q inverse times Q, where Q is the n by n matrix, whose jth column is the jth vector of beta. Okay, so we have that this is A similar to the matrix of this form. Okay, and we also know that the matrix D representing the linear operator LA with respect to beta is diagonal. Right? So what this tells us is that, in other words, if we have a basis of eigenvectors, then the matrix representing the operator with respect to it is similar to a diagonal matrix, right? So we know this fact from 115a. Now, what it tells us is that the columns of Q, of the matrix Q, form an orthonormal basis for Fn, right? Because again, the jth column is the jth vector of beta. Well, Fn in our case, Cn, it's the same, yeah. And so, by the previous remark, so this was, let me go back for a second. So this is remark 2 here. Yeah. So by remark 2, we get, in this case, that Q, so by remark 2, we have that Q star times Q is the identity matrix. Right? So we have Q star times Q is the identity matrix. And these are the square matrices, right? And Q is a square matrix. And we know that for square matrices, then we also have the product in the opposite direction. Q times Q star is also the identity matrix, right? So it follows that Q is unitary. And also that Q star is equal to Q inverse. Okay, so we get this. And the conclusion is that we have written D equals Q star times A times Q, right? And Q star is unitary. So by definition, this means that A is unitarily equivalent to a diagonal matrix. Okay, so this proves the converse implication of the theorem and concludes the proof. We have an analogous result for orthogonal equivalence in the situation of matrices over the real numbers. So this is theorem 620, which is the analog of the theorem we just proved for matrices over the real numbers. Okay, so assume A is a matrix, n by n matrix over R. Then we have that A is symmetric if and only if A is orthogonally equivalent to a real diagonal matrix. Okay, so we have an equivalent analogous result for the case of reals, and here the proof is also going to be a homework problem in the next homework. So the proof is similar. So proof similar to the previous theorem, to theorem 619, but the task here is now to use instead of using the characterization of unitary operators, right? Normal operators. So here you have to use the corresponding results for real inner product spaces. Okay, so similar. See homework 6. It's going to be on the next homework. Okay. All right. So we have this, and the final remark. The final result, theorem 621, this is going to be the analog of Schur's theorem, but for matrices. So this is a matrix form of Schur's theorem, which, remember, was an important result for linear operators, whose characteristic polynomial splits. So Schur's theorem told us that in that case, the matrix representing the linear operator with respect to some orthonormal bases is upper triangular, right? So we have an equivalent analogous statement for matrices now. So assume that A is an n by n matrix over F, okay, such that its characteristic polynomial splits. Then we get a similar conclusion. Okay, so splits, let me be precise, over F, the field of scalars that we have here. Okay, then we have the following. A, if the field of scalars is the complex numbers, then A is unitarily equivalent to a complex upper triangular matrix. Okay. And in the case of the field of reals, so if F is equal to R, then A is orthogonally equivalent to a real upper triangular matrix. Okay. And this theorem follows from the Schur lemma for linear operators and the results we just obtained. right? So we have obtained this theorem 619, which tells us that a matrix is normal if and only if it's unitarily equivalent to a diagonal matrix, for example. And similarly, we have 619. So then Schur's matrix form of Schur's theorem follows from these results and the usual Schur's theorem for linear operators. Intuitively, what we're getting here is that in the case of when the characteristic polynomial splits, right, unitarily equivalent, you can think about it as a base change, where you change from one orthonormal base to another orthonormal base, right? In the same sense as like we had for similarity, which corresponded to base change. So here we can think about base change and remember unitary or orthogonality. So this kind of operators, it's operators that preserve distances. So similar multiplying by matrix of this form, you keep the distance, the norm, and hence inner product as well, as we know. So we get that one orthonormal basis gets changed to another orthonormal basis with respect to which you now your matrix has a simpler form now. Okay, so that's maybe the geometric intuition behind it. Okay, so this summarizes some of the main properties of matrices corresponding to unitary and orthogonal operators. So our next task is actually to understand to develop a deeper understanding of the structure of orthogonal operators. For this purpose, we will study special kind of orthogonal operators, namely orthogonal projections. And then we will have this very nice decomposition theorem, which tells us how to decompose an orthogonal operator into simpler ones, the so-called spectral theorem. So it's a very fundamental result about such operators. Some of you might have seen it, but now we're going to develop it rigorously with all the proofs, yeah? Okay, so this starts this new topic. Well, it naturally flows from what we just discussed, but in some sense, it's now a new topic. So orthogonal projections and the spectral theorem. Okay, so the very fundamental result about the structure of orthogonal operators. So you've already seen, of course, projections in various forms, right? So let's make it precise what we mean by projection, first of all, in a general vector space. So definition one, so we say that a linear operator T on some inner product space V. In fact, for this part, actually, vector space is fine. We don't even need, well, for this part yet, but you'll see, okay? So we'll say that such linear operator is a projection on the subspace W along the subspace W2, sorry, on W1 along W2. Oh, I forgot the word projection, excuse me. So I said it, but I didn't write it. So we say that a linear operator T, is the projection on W along W2, okay, where both W1, W2 are subspaces of V, such that V is the direct sum of these two subspaces. So V can be written as W1 direct sum with W2. Okay, so in this case, the linear operator T is a projection. If whenever we have vector X written as the sum X1 plus X2 with Xi an element of Wi, and we know, of course, since it's the direct sum, every vector in the space V, every vector X in the space V can be written as a sum of right of a vector in W1 and of a vector in W2, and moreover in a unique way because it's the direct sum. So whenever we have this, then the result of applying T to X is simply X1. Okay, so we forget the component corresponding to W2. That's why we talk about projection on W1, because what survives is only somehow the coordinate of the vector corresponding to W1, and the one corresponding to W2 disappears. Okay. As it would for the projection, right? Like if I draw the picture, the usual projection, for example, if this is W1, this is W2, so we know that R square is the direct sum of these two subspaces. And then if you have some vector, X, then if we take the projection, well, so first of all, this vector can be written as the sum of X1 and X2, right? So the sum is exactly X. So the projection corresponds to just this component. Okay, but this makes sense for any choice of the subspaces, as we just defined. So that the sum, direct sum is the whole space. Okay, so this is one. We defined projection. Now, part two, by homework exercise, we already know that in this situation, the range of T is going to be W1, and the null space of T is going to be precisely W2, right? And then we're going to say that a linear operator T on V is a projection. Okay, so we'll simply say that a linear operator is a projection if there exists some spaces, subspaces, W1, W2, satisfying the definition above for T. For T, right? So we have this. In this case, we will just talk that we will just say that the general operator is a projection if there is some choice of such subspaces for which we have that this is projection on W1 along W2, all right? And part four, again by homework, we know that a linear operator T is a projection if and only if T is equal to T squared. So T is equal to the composition of T with itself, right? Okay. So we have this equivalent characterization of being a projection. So now we want to strengthen it and introduce the notion of orthogonal projection. Okay, so note a warning, an important warning here. So if we can write V as W1 direct sum with W2, but assume we can also write it as W1 direct sum with W3 for some different subspace W3. So even if we have this equality, this does not imply that W2 is equal to W3. Okay, so it's possible to write the same space as the direct sum of subspaces in many different ways. Like here, we have taken the X and the Y axis, right? But you can also take any other pair of subspaces. Like I can take, for example, this line and this line. These are two subspaces, and the whole space is still the direct sum of the two. Okay, so this doesn't apply this equality. So we see from this remark that W1 alone does not determine T uniquely, right? So it's not enough to specify projection. It's not enough to say on which subspace it projects. We also have to specify along which subspace W2 it projects onto W1. Just saying projection onto W1 alone, there might be many different ones. Like it doesn't determine the projection T because of what we just remarked, right? Okay, so to fix this, we can strengthen projection, the notion of projection, to the notion of an orthogonal projection. So this is a notion which only makes sense if we have inner product space structure. So now let V be an inner product space, okay? And we let T be a linear operator on V, which is a projection. Okay. Then we say that T is an orthogonal projection okay, if we also have additionally that the orthogonal complement of the range of T is equal to the null space of T. And similarly, we have that the orthogonal complement of the null space of T is equal to the range of T. Okay, so we have these two additional requirements for a projection, in which case we will call it an orthogonal projection. Let me see. So if T is a projection, there is a unique direct sum decomposition. No, that's the point. It's not unique. That's what we just said, that you can have two different decompositions, okay, as a direct sum of V. They can be two different. That's the whole point why we need to introduce orthogonal projections to rule out this possibility. With orthogonal projection, we're trying to rule out this possibility. So we want to say that orthogonal projections are those projections for which, if we know onto which subspace it projects, then there's only one, then it specifies along which space it's projecting. And this is going to be ensured by these two additional conditions in the definition of orthogonal projection. Okay. All right. So far it's just a definition. We'll see many nice properties and observations about it in a minute. But for now, just let's go with it. Okay. Just go with me for a minute. So again, a projection is orthogonal if we have these two conditions. The range space is the orthogonal complement of the range space is the null space and vice versa. So basically we are saying that the range space and the null space are orthogonal for this map. Okay. So first of all, we have the following remark about this. So from 115a, we know that if V is a finite dimensional space, okay, and W is a subspace of V, then the orthogonal complement of W, if we take again the orthogonal complement of it, what we get is just W itself, right? So taking the orthogonal complement twice, you get back to the same subspace in the finite dimensional case. Okay. Hence, each of these two conditions, excuse me. So what it tells us then is that each of the two conditions in this definition, in the definition of the orthogonal projection, already implies the other one. Okay. So we have that, for example, if the orthogonal complement of the range of T is equal to the null space of T, then we also have that the range of T is equal to the null space of T. Well, let me write it in the opposite order. So we get that the range is equal to the range of T orthogonal complement by what we just said, right? But this then is equal to n of T orthogonal complement, right? So we see that if the range is orthogonal to the null space, then also we have that the null space is orthogonal to the range, and vice versa. Okay, so this tells us that if you want to check that something is an orthogonal projection, you only have to check one of these two conditions. Then you have the other one for free. Okay, so this is the first remark. The second remark, however, that this is only true when the vector space is finite dimensional. Okay, so let me stress it here. So finite dimensional space, which has this condition with this property that the orthogonal complement of the orthogonal complement is just W itself. Okay. So, however, this remark is not true in the case of infinite dimensional spaces. So this is not true if the dimension V is equal to infinity. Okay. So finite dimensionality here is important. If you're checking, make sure that it's assumed, for example, in the problem or, well, in the question you're considering. Okay. To show you that this is not true, we have to consider some infinite dimensional inner product space. So we haven't touched on many actually in this class, but I want to give you an example here showing that this is not true of an infinite dimensional inner product space. So what's the example? We can consider the vectors, the inner product space V, which is denoted as little l square. Okay, maybe you have seen it in some other class. So what does it mean? So this means that the elements, the vectors in this space are given by infinite sequences. So now vectors are infinite sequences where AI is an infinite sequence of real numbers, okay, such that the sum of the squares of this sequence converges. So the sum is smaller than infinity, okay? So we take all possible sequences like this, all possible sequences which are square summable. That's why it's here, we have 2, it's denoted as L2, okay? All right, so it is a real inner product space with the following operations. Okay, so the sum, we define it in the natural way, just coordinate wise. So the idea is to define it in the same way as we had like for Rn, for example, but now it's R, but infinite sequences. So we take the sum of 2 sequences like this, Bi, I, and N. This is going to be the sequence, so that the ith element of the sequence is given by the sum of the ith elements of these 2 sequences. Okay, so we have this for all sequences AI, Bi in L2, and similarly we can define scalar product. So we take C times AI for a sequence I and N. This is just the sequence given by C times AI for I and N. Okay, so we have this for all A, I, Bi, and C in R in this case. Okay, and finally I tell you what the inner product is here. So the inner product of 2 sequences is given by the same formula as the dot product. So this is just the sum overall AI times Bi, where I ranges from 1 to infinity. Okay, so this is again an infinite series. I'm going to stop here today, but and I'll let you ponder about this a bit, okay? If you've never seen infinite dimensional vector spaces, this is a very good one to consider. So make sure that these operations are well defined. So to check it, you have to check that the sum of 2 square summable sequences is itself a square summable sequence, right? So you have to show that the sum of squares of AI plus Bi is going to converge, assuming that the sum of squares of AI and the sum of squares of Bi converged. So check that all these operations indeed satisfy the axioms of vector spaces and inner product spaces, okay? And next time we'll finish this example, so we'll see why this property of orthogonal projections, we do have to specify both conditions in the definition, as opposed to just one, like in the finite dimensional case. Oh yeah, and make sure that this is an infinite dimensional space as well, okay? So, I mean, maybe intuitively you can see, right? Because because like if it was just Rn, for example, but here you cannot choose a basis. So try to make sure, so rigorously check that this has infinite dimension, this as a vector space. Okay. So I'll stop here for today. Thank you very much. And we'll finish it next time. But I'll let you ponder a bit about why this is like a nice infinite dimensional vector space and why this is indeed an inner product. So all of this follows from the properties of convergence series that you probably know from some real analysis class. Okay. All right. So thank you very much.